imagine that you have a rope, and the rope is tied at one end to something solid, and you're holding the other end in your hand, kind of like a jump rope, right? That you've tied to something. If you shake the rope up and down, you might imagine it would look like, um, or it could look like this picture. Nope, like this picture right here. And if you shake the rope a little harder, you can actually get it to look more like, let's do this, more like this. And then at some time later, it might look like this. And if you shake the rope a little harder, when I say harder, actually what I should say is faster. Um, let's visualize this. It's this system right here. So if you're shaking the rope fairly slowly, it might look like the first image there. Right? And if you shake the rope faster, at some point you'll reach, at some specific frequency, you'll reach the second mode of oscillation. All right, so it's a higher frequency and a shorter wavelength. And if you wave this thing faster still, it's a higher frequency yet and a shorter shorter wavelength, and you reach this third mode of oscillation. Try it sometime. Try this with like a jump rope or a slinky. This works great with a slinky. These are called standing waves. All right, and you can see there are points on these standing waves that don't oscillate at all. Right, it's in the dead center of the second mode there. There are 2 points in the middle of the third mode that don't move. They're the points that cross on the images above. All right, so we often draw standing waves like the pictures in the top row, but what's actually happening are the animations in the second row. All right, and so that's what I'm going to draw over here. So we're introducing this idea of standing waves via example number 9. Right, and again, nodes are points that don't oscillate. So this is a node right here, and antinodes are points that oscillate maximally. So this is an antinode, and this is an antinode. And this second image is what we call the second mode of oscillation for this. And this first one is the first mode. Sometimes we call this the fundamental. And the second one, sometimes we call it the first harmonic and the second harmonic. Maybe the second harmonic and the third harmonic. That's more for musical instruments, and we'll talk about that in the future. So let's keep writing this. Let's see, how many nodes do we have for the second one? Well, there was one node in the middle for mode 2. So now there are going to be 2 nodes in the middle, and they're going to be equally spaced like this. And I'm going to choose, I chose a green color before, so we'll do that. So this is what this looks like at one time. And at another time it looks like this. And there's actually a time for this where it's completely flat. All right. If you were looking at this as a function of time, like we saw here, do you see that there's a brief moment for each one of these where all of the string is in one line, right? So the displacement is 0 for the entire thing, but the velocities at every point are different, and that's what causes this to keep going. Okay, so let's keep drawing this, or maybe we'll label these 2 nodes inside and an antinode at each of those lobes of this thing. Moving forward, we'll do one more. So instead of 2 points in the middle, there are 3 points in the middle, so we'll try to evenly space those and do some kind of green color for this. Fabulous. And we can label again the nodes and the antinodes. Okay, so if the total length of this string is L, what are the wavelengths for these? So I told you the way to access these modes is to oscillate these at different frequencies, right? So oscillating at a higher frequency should get us shorter wavelengths. Again, because the wave speed doesn't depend on frequency. The wave speed just depends on properties of the string. Okay. Remember that a wavelength is one full cycle. So we're just looking at, say, the green waves. So it's easiest to visualize for, let's use a different color. Salmon. Why not? It's easiest to visualize for the second mode here. Do you see that this length from here to here, that is a wavelength? Right, and for the second one, sorry, that's actually the third one, I have to go from here to get a wavelength. And for the fourth mode, I have to go from here to here. Again, I'm looking at, say, the green trace for each and saying, where does the green trace get back to where it started? Right? So the temptation is to say, oh, it's a peak-to-peak distance, and to do that. But that's a peak of the green trace to a peak of the blue trace. It's not a full cycle, it's only a half cycle. Okay, so can we come up with a mathematical expression? Well, I hope that you can see that for the fundamental mode up here, that's only a half of a wavelength. And if all of these strings are length L, then I can say for the top mode, let's switch, I like this color, we'll keep it. For the top mode, L equals a half wavelength. Or I can turn that around and solve for wavelength. Wavelength must be 2L. And for the second mode, actually, let's do this. Lambda, or L equals half lambda. So I'm going to bring that down here and write it right here and say lambda equals 2L for n equals 1. And here, lambda equals L. That's pretty straightforward. Really, let's see L equals lambda, just for pedagogical reasons. So then lambda equals L for n equals 2. And here it looks like L equals 3 halves lambda. Do you see that there are 3 halves of lambda here? So L equals 3 halves lambda. Or I can write lambda equals 2/3 L. Lambda equals 2/3 L for n equals 3. And we'll do one more. Looks like L equals 2 lambda here. So lambda is L over 2 for n equals 4. But it looks like I could build up then a general rule here, which is that, let's see, if I write the second one as 2 over 2, and I write the fourth one as 2 over 4, it becomes a little more obvious what I can do here. Looks like I can say lambda equals 2L divided by the mode, n. So we say the lambda sub n. Sometimes I use m for this. It doesn't matter whether you use m or n. They're just integers. Alright, so the general rule here is that lambda sub n equals 2L over n. Alright, and again, this works out. If I let, for the first mode, I plug in n equals 1, and I get 2L. N equals 2 gets me just L. N equals 3 gets me 2/3 L. It looks like I could also say, remember that wave speed is lambda times f. All right, and wave speed is not a function of frequency or wavelength. So when I change the wavelength, all I'm going to do is change the frequency. So this would be lambda sub in f sub in, right? But this should be true for 1, it should be true for 2, and so forth. All right, that means I could solve for f sub in as a function of in using this kind of setup. So let's do that. So v equals lambda, so let's solve. Lambda sub in is 2L over in times f sub in. So I could solve for f sub in. No. I could solve for f sub in here. F sub n is in v over 2L. In v over 2L. Make that 2 actually look more like a 2. This is kind of interesting because it means f sub n are equally spaced, and the spacing is v over 2L. It also looks like, yeah, we'll write it down here just for space's sake. I could call v over 2L, this is f sub 1, the fundamental frequency. And then I could write this as in times f sub 1. Okay. So let me summarize that. Let's see. This equation is useful. Let me even summarize it on a different page. We'll go back to scratch. Standing waves. Okay, for standing waves, and this is specific to standing waves with nodes on each end. Alright, this also works if you have an antinode on each end, but if there's an antinode and a node on either end, then this changes mathematically. So the wavelength for this, again, was 2L over n, and the frequency of each mode is n times v over 2L, or n times the fundamental frequency, where the fundamental frequency is v over 2L. Alright, we also know that v equals lambda f. It's lambda sub n, f sub n, and those have to be the same n, right? Again, it's got to be 1, 1, or 2, 2, etc. Okay, so let's talk for a second about wave speed. I've told you wave speed depends on the medium. So what if I know the medium? What if this is a rope? Well, okay. If we have a rope, what could this depend on? So I'm not going to derive this, but I'm going to say the properties of a rope are going to be, let's say, rope or string properties. Well, there are basically two things you can control about this. One is the weight of the rope. And what I really mean by that is the linear density. It's supposed to be an L, I promise. Linear density. So linear density is this Greek letter mu. We've used it before. This is what we're using for mass per unit length. So it's total mass divided by total length, right? Or mass of some section divided by some section's length. So things that have a high linear density are like the ropes that you would use on a sailing ship, right? Ropes that have a low linear density are like string that you'd buy, like twine, right? So the heavier the rope is, the harder I expect it to be to oscillate, right? Because mass is something's resistance to acceleration. So I expect wave speed to be inversely related to the linear density. By the way, the unit here would be mass, kilograms per meter. All right, the other property that we can talk about is tension, right, which is just T, obviously. And the more tense this rope is, the more tension is in the rope, the faster I expect the wave speed to be, because the rope is connected to itself, right, and so it oscillates. The force of interaction is that tension. So it turns out the wave speed for a wave on a string is the square root of tension over the linear density. And you know what? I'm going to change T to F sub T because T is also period, which is confusing. So I'm going to say F sub T. Great. That's great. So let's do one more example. Let's do this example. So example 10 says the fifth string on a guitar, the second lowest pitch string is an A, and the frequency of that A is 110 hertz. If the length of the string is 64 centimeters and its mass is 2.86 grams, what is the tension in the string? Okay, so what do we have here? We have frequency, we have length, and we have mass. So let's collect those things. The frequency, right? In fact, that's the fundamental frequency, is 110 hertz. The length of that string is 64 centimeters, and the mass of the string is 2.86 grams, and we're asking for tension. That T doesn't look like a T. Better. Okay. So it looks like I can find the mass per unit length pretty quickly, right? And I'm going to need that, but I'm also going to need wave speed. So let's actually gather those two things. Let's see. V equals the square root of ft over mu. So I have everything I need to get mu, mass per unit length, right? We'll say total mass divided by total length. Make that a capital M. But I don't have wave speed. So what else do I know? Well, I know that wave speed is wavelength times frequency. So if I knew the wavelength of this wave, then I could find the wave speed and then plug that into the original equation. So I have one more equation, and remember, a guitar string is just a wave. It's just a string that's connected at both ends, right? Tied down at both ends. So I have an expression for that. Lambda sub n is 2L over n, right? So I could find wave speed from that. Okay, so let's put it all together then. So I'm going to erase this to give myself a little more space. So 1, the mass per unit length is 2.86, let's do SI units, divided by 64 centimeters, 0.64 meters, is 4.47 times 10 to the minus 3. 4.47 times 10 to the minus 3 kilograms per meter. So there's my mass per unit length. That's useful. What about my wave speed? Wave speed is lambda 1 times f1. f1 we have directly. Lambda 1 I have an equation for. So I'm going to say, I'll just do lambda 1 times f1. lambda 1 is 2L over 1, right, times F1. So I can plug that in then. So 2 times length is 0.6, I'm going to do a little better, 0.64 meters, times that frequency is 110 hertz. Hertz is an SI unit because it's 1 over seconds. All right, so what I get for the wave speed on this is 140.8 meters per second. Does that track? Yeah, it does. Because 2 times 0.64 is a little over 100, so a little over 1. So a little over 1 times 110 is going to be a little bigger than 110. Turns out to be 140.8 meters per second. Great. So we are almost there. So then step 3 here is that V equals the square root of tension divided by mass per unit length. So I just plug in 140.8 meters per second. I'm going to square that side to get rid of the square root, equals tension divided by the mass per unit length, which is 4.47 times 10 to the minus 3 kilograms per meter. So the force due to tension is 140.8 squared times 4.47 times 10 to the minus 3. It turns out to be 88.6 newtons. So if you were looking to tune this guitar and you knew this bit of information, you could actually tune it by measuring that force. Right? There are easier ways to tune this. You can actually measure the frequency of what's coming off, and you could feed back to that. But if you really wanted to, you could tune a guitar by tension if you know exactly what kind of strings you have on there and exactly the length between the bridge and the top of the guitar. So we could also ask, what is the frequency of the third harmonic for this string? So when you pluck a guitar string, what you hear is the fundamental. But you can force the harmonics to come by damping out the fundamental, right, by touching the string in certain spots. So you could get the third harmonic. So what is the third harmonic? That's n equals 3. What is that frequency? Well, F sub n is n times F sub 1, right? So it's just 3 times 110 hertz, or 330 hertz. Okay. We could also ask, what is its wavelength? Well, just like we had before, lambda sub n is 2L over n. So we could say 2 times 0.64 centimeters, just meters, divided by 3. What I get is 0.43 meters. And if you take the product of those, you get the wave speed, just like we did above.